Okay, citizens, welcome back. This is the big one, so make sure your RAMs are in place, your PPE's up to standard, and we'll just crack on with the complete system. So, here we go then, the basic refrigeration cycle. So, there are four main components in any refrigeration cycle. They are the compressor, the condenser, the evaporator, and the expansion device. Now, here we are again with the compressor, condenser, evaporator, expansion device, and in this instance we have an air-cooled condenser which has air on and air off, hopefully a little bit warmer, and brine on to the evaporator this time, and brine off, hopefully a little bit cooler. So here we start at the gas leaving the compressor, and we have a high pressure and high temperature gas leaving the compressor. And why is it high temperature? Because of frictional and compressive heat gain. Now, if you were to ever put your finger over the end of a bicycle pump and pump it, it gets hot, and that is the reason: friction and compressive heat gain. So the hot gas enters into the condenser, and because we know that within the condenser we have a phase change where it turns from a high pressure gas, hopefully, down to a high pressure medium temperature subcooled liquid leaving, and then it hits the expansion device, whereas there's a sudden pressure drop. As it leaves the expansion device, it's a massive pressure drop, so it tries to turn back from a liquid to a gas and becomes a two-phase mix. That then enters the evaporator, and as we know, it needs heat to change from the liquid to the gas, so it draws that latent heat from the brine on, and the brine off is hopefully a lot cooler. If we've done everything correctly and we've set up our expansion valve, etc., correctly, the gas leaving the evaporator will be a low temperature superheated gas. And why do we want superheated gas? Because the compressors don't like pumping liquid. So here we go on to the complete cycle. As you can see, the refrigerant is happily going around the system because the compressor is driving it. We have the heat absorption within the evaporator and the heat rejection in the condenser. So in other words, the heat absorbed from the brine is rejected to the outside air. Now I'm going to introduce you to the basic refrigeration chart, which we know as a Mollier pH chart, which is pressure enthalpy. And the reason I'm doing this is because in your F-gas you're going to need to know a fair bit about this. Now this is what a pH chart looks like. It looks pretty daunting, I know, but if we break it down into different sections, it's not too bad. At the bottom, on the scale on the bottom, we have the enthalpy, which is loosely described as total heat. That's the sum of your latent heat and your superheat. And on the left hand side we have pressure in bar A. Remember the difference between bar A and bar G. So looking at this, you can see there are three main areas of the chart. We've got these two lines, which the one on the left is the saturated liquid line, and the one on the right is the saturated vapor line. Anywhere within that part, the green part of the diagram, the liquid is in a two-phase mix condition. Anywhere below that, to the left of that line, is the subcooled liquid line, and anywhere above that line in red is the superheated vapor line. We also got the critical point of the refrigerant. Now if we break the basic chart areas down, it makes it a little bit more simple. We've got the saturated liquid line or the bubble point, as we know in gases that are zeotropic. Zeotropic means that they will separate within their component parts. And we have the saturated vapor line, which is the dew point. Here we have again the two-phase mix area, the subcooled liquid, and the superheated vapor. Now, anywhere between the superheated vapor walking towards the saturated liquid line, the liquid is changing to vapor, as it would in a condenser. And on the other hand, we've got the liquid turning to vapor going from the saturated liquid line to the saturated vapor line. Now these lines here that you can see, they are known as the lines of constant dryness, and anywhere along that line you get a variation of liquid to vapor ratio. So there you can see if the refrigerant's on that line, it's 10% vapor, 90% liquid. Here it's 50% vapor and 50% liquid. And towards the end there, it's 90% vapor and 10% liquid. So if it ever goes across that line, it's superheated. And if it ever goes below that line, it's subcooled liquid. Here we're showing the lines of constant temperature. You can see from here, follow the lines, say 40 degrees up there, and you'll come to use those when we come to draw a chart. Here we have the lines of constant entropy. I'm not going to go into that at all. There's no need to know that for this, but you must be aware that that might be a question in your F-gas test. And the same here for the lines of constant specific volume. We're not going to touch on those here, but again, be aware they may be in the F-gas questions. Okay, so let's start with the simple or basic cycle. We've got a saturated liquid line on the left and a saturated vapor line on the right. Here we have the compressor. So at the entry point to the compressor, the suction of the compressor, it then gets increased in pressure and temperature until it exits the discharge of the compressor. The gas now enters the condenser, and as it travels through the condenser from right to left, it is changing from a gas back to a liquid until it gets to the point, at the furthest point on the left, where it's hopefully all liquid, and that then enters into the expansion device and drops in pressure and very little temperature drop, and enters the evaporator, and as it moves along the evaporator towards the compressor, it's changing from a liquid back to a gas until it gets back to the compressor suction again. At this point, hopefully it's all gone back to being a gas, so therefore we're not going to damage the compressor. Okay, so that was a theoretical cycle. Let's have a look at a more realistic working cycle. We start off again with the compressor. We're raising temperature and pressure into the condenser, where it's turning slowly back from a high pressure gas to a high pressure liquid. That then enters the expansion valve, where there's a massive pressure drop but no real change in temperature, and it then goes into the evaporator. Now, as it's moving from left to right, it's gaining heat and it's boiling back and changing to a gas, and hopefully when it goes back into the suction of the compressor, it's purely superheated. Now, we have this part here which we call the refrigeration effect, and this part here is the work done. So that's the energy that's put into the compressor, and the RE is the energy that's collected through the evaporator. These 2 points here matter quite a lot. You've got the subcooling and you've got the superheat. Okay, so we look at our normal standard diagram and we see what's going to happen now if we raise the head pressure. Now, on our standard diagram, we have the refrigeration effect and the work done, and that is a coefficient of performance, which is a ratio of the refrigeration effect divided by the work done. Now, in this instance, you're probably looking at about 4 to 1. So it's 4 units moved on the refrigeration effect and 1 unit put into the compressor. Now, if we were to increase the head pressure from 10 bar to 20 bar, it would have the effect of this. So that would go much higher, temperature and pressure. That would be much less. That would go down. And there you would have your new cycle drawn, showing that you have a decreased refrigeration effect and an increased work done. Now, that ratio now is going to be probably just over or just under even 2 to 1. And that's the effect of head pressure. And you need to know that that is a big part of the F-gas. A quick talk on the efficiency of a system. If you go to do your F-gas, they're very hot, and you knowing that an inefficient system uses a lot more energy, so therefore you need to know what the causes are, etc. Now, if you look back to our system with the increased head pressure, you can see that it's much higher here and much shorter here. Now, those two lines, the closer they are together, the more efficient the system is. So, for example, in here we have possibly a dirty condenser, and it's given us a false raised head pressure, so the system's a lot less efficient than it should be. Now, what the F-gas people are looking for is to know that you are aware of this and you can hopefully prevent it. Well, let's have a look at drawing a pH chart. You can see at the bottom there, I've listed some of the parameters with suction pressure, discharge pressure, suction temperature, discharge temperature, and the liquid line temperature. So we'll start off by drawing a line along the 3-bar line. Remember, bar A. So there you go with that line. And now we're going to draw a line along the discharge pressure, which is the 10-bar line. There we go. We're going to mark the suction temperature, which we've measured at 10 degrees centigrade. There is the air. And we're going to mark the discharge temperature, which is 55 degrees C. So we've now put that, and then we join the points. And there you go. That's the compressor line. And now we're going to mark the liquid line temp, which we've measured at 30 degrees C. And there's that point there, and we're going to draw a line straight down because we're not going to worry about too many pressure drops in the system. And there you go, that's that drawn. And now all we do is tidy it up, and you can see here we have the superheat region, and there we have the subcooled region, and that is your chart. Well, I'd like to thank you all for watching, and I hope very much that it helps. And if you thought it was useful, maybe give it a like. And if you would like anything specific to be covered, please put it in the comments below, or you can email me at david.finleynh3@gmail.com. Well, happy refrigerating, citizens.